Okay, so let us learn about central limit theorem, which is the basis of all the hypothesis tests. So let's imagine that we have a population. Now let's say I want to know the average height of the population of the world. Okay. This is the total population of the world. Now I can't go and collect all the data of all the people in the world. Let's say I'm talking about heights of male, average heights of male in the world. Now, because I can't go and collect all the heights, so what would I do? I'll take a sample. I'll collect a sample. Let's say I take 100 samples, and I find that average height of 100 people is 174 centimeters. And it has a standard deviation of, let us say, 5 centimeters. Now, based on that, I can say that my average height is 174. I'm not so sure about it, but maybe I can say, well, yes, I think so. It is 174. And I can also predict the overall population of the world. What will be the overall population of the world? Our good old plus minus 3 sigma will come to our rescue here. So we have got 1 sigma, 2 sigma, and 3 sigma, minus 1 sigma, minus 2 sigma, and minus 3 sigma. And if you look at the values, so you look at the values, you'll get 179, 179 and 184 and 189. And here it will be 169 and 164 and 159, which is of course the lower control limit and upper control limits. So this is the overall population of the world. 99% of the world population, male world population, lies within 159 to 189. I'm predicting about maybe 1 billion people. Up to here we are sure about it. We know from where these values are coming from Gaussian curve, Carl Friedrich Gauss. Remember that person. Now, if you want to challenge me, you ask me what is the average. Now we are looking at the average. We are not looking at the distribution. I'm not asking about the distribution of the heights. Distribution of the heights is 159 to 189 centimeters. But now if I'm asking you about only average, what is the average height of people in the world? Looking at the sample, you may say 174, or I may say 174. But how sure I am? How sure I am? You can challenge me. You can say, no, so sorry, it is not 174. It is something else. Are you sure about it? Is it 174? I say, yeah, I'm sure about it. I've collected the samples. Then you will say, well, let me prove you wrong. You collect another 150 samples, or maybe let us say 100 samples. And you tell me, see, I told you you are wrong. And you say, it's 175. Again, you can prove me wrong by collecting another samples, and this time it is 173. But as you go on collecting samples from the same population, you will keep getting values 174.5, 172.3, and so on and so forth. So one phenomenon which you'll observe would be the averages. Now we are talking about averages. I'm talking about averages. Please remember averages. The averages keep on collecting the data, averages will be somewhere, sometime 174, sometimes 173, sometimes 175, and sometimes, so keep on collecting the data. They will appear to be hovering around some value. It will appear as if they're tending towards some value. Like sometimes here, sometimes there. And it will also follow normal distribution curve. Central limit theorem means averages of averages of a sample drawn from a population. Keep on drawing samples and keep on getting the averages. Averages of the samples drawn from the population will always follow normal distribution. Okay. Averages of the samples drawn from a population. Even though the population is not normal, it will always follow normal distribution. Now here the population is normal, we know that. But even though if the population is not normal, still averages will always follow normal distribution. So if I represent this on this curve, it will be something like this. The averages of the sample will follow normal distribution. So now, because it's following the normal distribution, I know then it will have its own standard deviation. Now the standard deviation will be different from what I got here. This is the sample standard deviation, which is estimating the population. This 5 is the sample standard deviation of the population, whole population variation. Now, if I'm interested in getting this standard deviation, which is of the mean, standard deviation of the mean, we call it as standard error of mean. I want to differentiate. Now this also will have its own standard deviation. This will also follow plus minus 3 sigma, plus minus 3 sigma, right? So this also follows plus minus 3 sigma. Now here sigma, I want to differentiate the sigma standard deviation from this standard deviation. It is a different one. So we call it a standard error of mean. Standard error of mean. It's like, how much error is in the mean. This is the error in your mean, isn't it? Error in your mean. Keep on collecting the samples, you'll keep getting the error. Some little bit of error will be there. So now I will refine my statement. Now if you ask me, what is the average height of males population in the world? I will say 174 plus minus something. Plus minus something, some error. Now, if I want to be 95% sure, so it will be plus minus 2 times the standard error of mean. 2 times standard error of mean. 2 sigma here, 2 sigma there. Okay, so that is what I will report. I will report plus minus 2 times the standard error of mean. Plus minus 2 times standard error of mean. Now how to calculate the standard error of mean? The formula for standard error of mean is standard error of mean is S divided by square root of n. N is the sample size, where n is the sample size. This is the n. N is the sample size. So n, if n is large, n is very large. Suppose n is very large, the standard deviation in the mean will be very, very less. It will be very less. Certainty in your estimation will be very high. If n is very small, standard error of mean will be higher. Okay, so if my sample size is very, very large, my certainty increases. If it is infinite means n is very large, like 1 billion. I have all the samples. There is no error. It will be zero. Infinity, anything divided by infinity is zero. So standard error in the mean is zero. That means there is no error. I will get the mean of the whole population of the world if n is very, very large. But of course, I will not go on collecting 1 million or 1 billion samples. I'm not going to do that, isn't it? I've got other important works to do. So what I would do, I'll collect a small sample and I will also report the error. I will say I collected 100 samples and I will also tell that no, this is my error in my mean estimation of mean. So here in this case, if I take the first example, standard deviation is 5 and square root of n is 100, n is the 100. So it will be 0.5. So in this case, I'll just collect one sample. And I'll say, well, you are interested in knowing the average of the whole population of the world. What is the average of the whole population of the world? I'll tell you. It is 174. 174. Then you say, are you sure? Oh, no, I'm not sure. Plus minus 2 times standard error of mean. Standard error of mean. 2 times standard error of mean. Plus minus 2. Remember, plus minus 2 standard deviation is 95%. So I can say I'm 95% sure, 95% confidence interval of mean is 174 plus minus 2 times standard error of mean, which in this case is plus minus 2 times 2.5. Standard error of mean is either 0.5, means 174 plus minus 1. Or if you want the interval, 173 to 175. So I can say with a 95% confidence that the average of the human population, males in the world, is 173 to 175. I'm 95% sure. Now this information is fair enough when I'm trying to estimate the average. Now similarly, call center, I want to estimate the average call handling time in a call center. I will not collect 100,000 calls which you make every day. I'll just collect 100 samples, and while reporting, what I will report? I will report the average of the sample with confidence interval of the mean. Now, if you remember, when you did your first graphical summary, you always got one confidence interval of mean. It was this mean which we were talking about. So 173 to 175 is the confidence interval of the mean. Mean means averages. Remember, 173 to 175 is the mean average, and 159 to 189 is overall population. We're talking about the variation in the population. That's different. Please remember, that's different. And this is for the mean. Now I can make my calculations. So now, suppose someone says, I feel evolution is taking place, and in 1980 we collected some samples. The height of males around the world was, I found that sample was 173.5. okay, and in 2020, after 40 years, I collected another 100 sample, and now the average height of the sample, earlier it was 173.5. Earlier it was 173. 173.5. Now I got a new sample, and wow, average human height has increased by 1 centimeter. I'm claiming that. Now I have to test the hypothesis. Mostly, your manager, how he makes a decision, he's mean-minded always. Oh, last month's average sales was this month's average sales is higher. Wow, very good. He never does a t-test. He never does a z-test. Never does. But black belt is a black belt, isn't it? He says, sorry, sir. What do you claim? What are you saying? Well, I feel I collected one sample in 1980, and average was found to be 174, let us say. Now I collected in 2020, I found 174.5, and I feel, evolution is taking the average of human heights. It's increasing. He will say, sorry, sir, let me test my hypothesis. Let us imagine that null hypothesis mean is 174. And what are you claiming? It has become more than 174. That's what you are claiming. You're saying it has increased. Okay, let me test. And you collected the data. Okay, let me collect 100 samples, 200 samples. And it was 174.8. Most of the people say, yeah, 174.8 is more than 174. So height has increased. But you are a black belt. Say, sorry. Let me do a t-test, one t-test. So this is a 173, 162, 179, 181, 174, etc., etc., etc. And of course, the average of this was 174.8. But you are not looking at this average. You are doing a 1T test, and you find it is 174. You say, go and have a look at p-value. P-value is point, let us say, 30. Black belt will say p-value is 0.30. P is high, null must fly, and because my statistics professor told me P is high, null must fly. Mu is equal to 174. It has not increased. Then there may be an argument. People may argue, how can you say that? I clearly collected the sample. In fact, I collected the sample. I saw that 174 with my own eyes. I calculated with my own hands. It is 174.8. It has increased. But black belt will say, no, sorry, p-value is high. Sorry, it is not increased. It's the same. Well, what exactly black belt is telling is, you got 174, okay. Imagine that this height is really 174. All the people were really 174. That's my hypothesis. But if you are 174, will you always get 174? No. When you are 174 doesn't mean you are 174 always. You'll never get. You may get this. You may even get, see this actually, if you remember, this never touches the x-axis. Even you may get 180 also. There's a probability, but the probability is very low. Probability of getting 180 is very low. That probability is how much? Probability is getting 180 If you are 174, probability of getting an average from a sample drawn from this population will be a 0.00001, very low. But looking at the data, probability of getting 174.5 or 8 or 174.8, yeah, is how much? Let me see. 174, 4.5, 175 here somewhere. Probability is very high. This probability is, there is a good probability. P is 0.30. This is that P value. P is probability of getting that value if your null is true, is very high. How about if I had got 174.2, it would have been higher. P value would have been, let's say, 0.40. You will be 40% wrong if you reject null. So better accept null that you are 174. So at 174.8, the P probability that you are 174 is how much? 30%. And you don't want to go wrong 30%. You already decided alpha value is how much? 0.05. I can go wrong up to 5%. Beyond 5%, I'll reject null. So as soon as you I'll make my decision based on that. Okay, fine. What do you want to say? Am I 174 or more? Have I increased? Well, give me a sample. Sample is, sir, 180. 180? If I were 174, probability of getting 180 is very, very low. P is low. Null must go. You are not 174, sir. I am really sure. You're not really 174. I think height has really increased. But suppose you get 174.2. Oh, sir, although 174.2 is higher than 174, but still, if you were 174, there is a good probability that you can get 174.2. Probability is high. You will be wrong, sir, 40%. Do you want to go wrong 40%? You are making a decision based on that. You won't be wrong, right? So that means better accept null hypothesis. Okay, so this is how we do our this is what exactly is happening in our test. Now if you recall, the samples formula is also, this, if I take this expression 174 point plus minus 2, what is this expression? This expression I can replace 2 times standard deviation, I can replace by delta or d. We call d in Greek, right? We have d means delta, Greek, d. If I replace this with d, d means the error, total error I can accept. Here, how much is the error I've accepted? How much error I have accepted? 1 centimeters. So if I replace this with the d, if I just express this as d, what is the d? D is 2 times standard error of mean. D is 2 times standard error of mean is square root of n. If I take square root of n here, 2 times standard deviation divided by t. If I square both the sides, so this is my sample size formula. Sample size formula. How many samples should I collect to estimate the average call handling time in my call center. How many samples should I collect to estimate what is the average call handling time in my call center? Well, I'll tell you. Sir, please tell me first, what is your standard deviation of the calls? What do you mean by that, standard deviation? I don't understand standard deviation. I'm not a statistician. Okay, so don't worry. Give me 30 calls. Just give me a sample of 30 calls. I'll estimate. And I estimate that average average time is 300 seconds. Standard deviation is, let us say, 30 seconds. So I estimated, by taking 30 samples, I estimated the standard deviation, and I'll put S as the standard deviation. Then I'll say, sir, how much error, how much is your D, how much is your error, how much you will accept, how much error you would estimate, you will accept in the estimation of your mean. Now, what do you mean by error? I don't want any error. Sorry, I don't want any error. Sorry, sir, you have to have accept some error. Well, no, I don't want any error. Okay, sir, then please collect all the samples of all the, you're making 100,000 calls every day. Please keep on collecting, and you'll get average call handling time without any error. Oh, well, I don't have any time to collect 100,000 calls. Then, sir, please accept some error. How much error you would accept? Okay, no, can you explain me what do you mean by error? Okay, so I'll tell you. I will give you a sample size that please collect 50 calls. Now, if you collect 50 calls and you get that, 50 calls give you an average of, let us say, 300 seconds. Please remember, sir, this 300 seconds is the average of these 50 calls. But the 100,000 calls are not 300 seconds. 100,000 calls are average would be 300 seconds plus minus 10 seconds. Are you okay with this error in your estimation of mean 10 seconds? Oh, well, 300 seconds, 10 seconds should be okay, fine. Okay, sir, then that is your D. And your number of calls should be 36. Just collect 36 calls. Whatever you get, if you get 200 seconds, please report the mean as 200 plus minus 10, because you told me your error estimation 95% error estimating band is 10. So please report that in my call center, my average call handling time is not 200 but 200 plus minus 10 seconds, which is fair enough. And I'm just making, look at the advantage I'm having now. Just 36 samples, I can predict about millions of calls. The sample size doesn't depend on the population. Okay. So this was the sample size for the continuous data. Now remember, the standard deviation of attribute data, it follows, actually attribute data follows binomial distribution, and standard deviation of attribute data is P into 1 minus P, where P is proportion defective. So if I substitute this formula into this formula, what will happen? So N is 2 divided by D square, and S I'm taking out. Okay, or if you want, I can keep it simple. 2 into square root of P into 1 minus P, because now it's attribute data, and this is my standard deviation formula. So this becomes 2 divided by D. Square of a square root will remove the square root, so this becomes my sample size formula for the attribute data. And attribute data sample size formula is P into 1 minus P. Now, how many calls I should audit I want to know the call quality. How many calls should I audit? Well, if you want, I can give you a sample size, but please tell me what is the quality of the call today? How many calls you are, uh, uh, what is the quality of calls? Oh, that is your P, proportion defectives. P is proportion defective. P is proportion defective. Well, my call quality is around, let's say, 80% today. Okay, 2 divided by square point 2 proportion defective. 80% quality means 20% defective, so 0.2, and 1 minus P is non-defective, which is 80%. 1 minus 0.2 is 0.8. Now, sir, how much is your D? How much error you can accept? What do you mean by error? I don't want any error. Well then, sir, please keep auditing, keep listening to all the 100,000 calls. There won't be any error. Well, no, I don't have time. No problem, sir. I'll give you a sample. Now, if I give you a sample size, please audit 200 calls. If you audit 200 calls and you get a quality of 80%, please let it be known that it is not 80%. 80% is for that sample of 200, but all your 100,000 calls, 80 plus minus 3%. Are you okay with that? Are you okay with this uncertainty in your estimation? Well, yeah, it's call quality. I want to make a judgment about my call quality. I think fine, 80. Even if I know today I'm at 80 plus minus 3%, I can have a goal of making it 90 plus minus 3%, and that's fair enough. So it's okay. I'm fine. Okay, sir, then your D is 0.03. That is 3%. And then after this, you do the calculations, and whatever is the number, I'm not calculating, but let's say if the number is 400 or so, so that becomes our sample size for, of course, I've not calculated, so whatever is the number, that number will be the sample size, which I will give it to the call center. Now, interesting phenomena about this P into 1 minus P is P into 1 minus P. Let us have a look. If P is 0.2, 1 minus P is 0.8. If 0.3, this is 0.7. If 0.4, this is 0.6. If 0.5, this is 0.5. If it is 0.6, if it is 0.4, if it is 0.7, it is 0.3. So maximum value of this expression is this. It can never go beyond 0.25. So what you can do? I don't even want to know your P into 1 minus P now. P into 1 minus P, I can take the maximum, which is 0.25. Because P into 1 minus P can never go beyond, under any circumstances, more than 0.25. And if I accept 3%, 3% uncertainty in my estimation of the quality or defect or defectives, this number will be around 1100. So that is why we keep telling that 1100 is the maximum sample size for attribute data. So when you want to estimate or understand who is going to win the election in US, without going to the, before the election date, of course, I just go to 1100 people, random, of course, the population should be randomly selected, and ask them, and based on 1100 people, I can estimate the winner. This is the power of the statistics.